let's talk about what matrix inverse means, when a matrix can be inverted, etc. You can think of numbers as though they are transforming other numbers. For instance, if I give you a number 5, let's say that is a transformation on some other number that you're dealing with. So 5x is a transformation. If I take x to be 2, then you get 10 as the output. Now 1 over 5 would be the inverse of that transformation. In other words, if I give you 10, then you can apply the inverse transformation, which is 1 over 5, on it to get 2. So that would be the reverse of the transformation. 5 applying on 2 gave you 10. 1 over 5 applying on 10 gives you back 2. We saw this idea in the elementary matrices or elementary operators. The inverse of an elementary operator was the one that did the opposite of what the elementary matrix did to the matrix that it was working on. We are kind of limiting ourselves to square matrices as of now. So the definition is this. If you apply a matrix on something and then apply its inverse, they kind of nullify each other. It's as though you did nothing, which means it's as though you multiplied the original thing by I. If you can find a matrix A inverse such that A inverse A and A inverse both equal I, then A inverse is the inverse of A. So the fact that you're multiplying on the left and on the right by the same matrix A inverse implies that both A and A inverse are square matrices of the same size, and so is I. Now what does that mean? Our original equation was Ax equal to B. Now suppose you multiply that by A inverse on the left. So A inverse Ax, that becomes A inverse times A times X, because as you know, matrix multiplication is associative. You can group the operation any way you want. And now we know by definition of the inverse that A inverse A is I. So this guy here becomes I. And now you know by the definition of identity matrix that I times anything is that anything. So it's just X. And that was applying A inverse on the left hand side of that equation. So you have to apply it on the right hand side. So X is equal to A inverse B, multiplying the right hand side of the equation on the left by the same matrix. So in other words, Ax gave you B, A inverse B gives you X. So that is the inverse. For now, we're going to say that it's defined only for square matrices, A in R n by n. It turns out that not all matrices are invertible. The condition for invertibility is that the determinant not be equal to 0. If the determinant of A is not 0, then the matrix A is invertible, a square matrix. That's why you can talk about the determinant. It's a necessary and sufficient condition. That means it's if and only if kind of situation. So let me say the if part. If the determinant of A is not 0, A is invertible. And if A is invertible, that says that the determinant of A is not 0. So it goes both ways. If A inverse exists, we may say that A is invertible, nice name. A is not singular. A is not degenerate. We like A. And it will turn out that if A is an n by n matrix, A will have n pivots in its REF. A has full rank of A is n. And the system of linear equations encoded in Ax equal to B has a unique solution because the solution is right here. Just say that X is equal to A inverse B, and that is the solution. We might say fancier things like A represents a linear automorphism, one-to-one onto kind of mapping, but that is just mathematics. But another thing that I want to say, A is row equivalent and column equivalent to I, meaning by performing a series of row operations, elementary row operations on A, you can get to I. The RREF of A is actually I. Or if you want to perform a series of column operations, which means a series of row operations on its transpose, you can again get I. Now let's look at some of the properties of inverses. Inverse of an inverse is the original matrix. That should be kind of obvious, right? In the world of numbers, inverse of 5 is 1 over 5. Inverse of 1 over 5 is 5. Scaling a matrix by S and then taking the inverse is the same as scaling the matrix inverse by the inverse of the scalar. Inverse of a scalar S is 1 over S, which is written as S to the power minus 1. So A inverse will get scaled by 1 over S. even though we use the same symbol here, 1 over s, we will not read this as a to the power minus 1 or 1 over a. So you can easily prove the statement that SA inverse is S inverse A inverse by just doing this. SA times S inverse A is S inverse because scalar multiplication commutes with matrix multiplication. In other words, SA is the same as AS, so you can actually move those things around. And S inverse is S divided by S, that is 1. And A inverse is I, so this is I. So SA is indeed the inverse of S inverse A inverse and vice versa. Then there is a product rule of inverses that reads much like the transpose case, AB inverse is B inverse A inverse. This has to be kind of obvious because in order to undo what AB does, first you have to undo what A did and then you have to undo what B did. Again, very easily proven using the associativity property of matrix multiplication. AB times B inverse A inverse is A times B inverse times A inverse, and this is I, so it's AIA inverse, and that is AA inverse, and that is I, indicating that AB and B inverse A inverse are inverses of each other. If a matrix is its own inverse, then it's called an involutory matrix. The example is a permutation matrix of a single row exchange. You swapped 2 rows and then you go and swap it again using the same permutation matrix. You get back the original matrix. The determinant of the inverse of a matrix is the reciprocal of its determinant, which is very nice because the determinant, as I mentioned earlier, behaves like the size of the transformation. The inverse having the reciprocal is kind of natural, and that's what you would expect. The determinant of A inverse is 1 over the determinant of A. So I can write it fancifully like this. Can you figure out how to prove that though? Actually, it comes from this statement here. You can take determinant on both sides. If 2 matrices are the same, then their determinants have to be the same. We know that the determinant of a product is a product of the determinants. So determinant of A times determinant of A inverse is 1, determinant of I. We talked about the double-sided inverses for square matrices. Then there is this idea of left and right inverses. Let's just go through this now, and we will probably circle back to this in some later chapter where it becomes more important. So a double-sided inverse, which is what we mean when we say inverse, that exists only for a square matrix with determinant non-zero. But for a rectangular matrix, when M is not equal to N, we can define left and right inverses when the matrix is full rank, meaning for a tall matrix, it's full column rank. For a wide matrix, it's a full row rank. So tall matrices, if it is full column rank, then the rank is equal to the number of columns. Then A transpose A is a square matrix. It's a smaller matrix because the number of columns is smaller than the number of rows. So N is smaller than N. So it's a smaller matrix and it is full rank. When it is full rank, the determinant is not zero and it is invertible. And you can invert it. Inversion basically means A transpose A inverse times A transpose A. This is what we're inverting. And so the inverses multiply to give you I. Now you can regroup it and just look at this part. That is something that is multiplying A on the left to give you I. So that is the left inverse. So this is exactly the way I would try to remember this formula for the left inverse, because A transpose A inverse A transpose sounds like a complicated thing to remember. But if you remember how you derive it, which is just one line, then you will always be able to reproduce this as a left inverse. So that is a left inverse. A transpose A, the whole thing inverse, times A transpose is the left inverse of A. But for a wide matrix, full rank means all rows are linearly independent. And this time A transpose is actually a smaller matrix compared to the wide matrix because M is smaller than N, got more columns. And that is full rank also because the rank is M, and that can be inverted. So now A transpose and A transpose inverse is going to be I. Now you can see something multiplying A on the right is giving you I. So we can call that guy the right inverse. So A transpose times A transpose, the whole thing inverse, is the right inverse of A. Left inverse, it turns out, that is more important for us compared to the right inverse because our matrices are tall and full rank in data science. Now we can talk about how you actually compute inverses. That would be the next little video.